Hello, sixth graders, and today we'll be discussing 7.4. We've got equations and inequalities for chapter 7. And for section 4, we're going to be talking about writing equations in two variables. For our learning target today, we have I can use tables and graphs to analyze the relationship between two variables, right? Really, this section is taking a look at some of these equations and saying, how do these equations, how does this algebra relate to anything in real life? And I think this section does a nice job of showing how those equations can represent real life situations. For our first key idea, it says an equation in two variables represents two quantities. A lot of times it's x and y, but remember, in real life, they represent something that can change in relationship to one another. So like as in x increases, y also increases, or vice versa, or it could be opposite of that. A solution, so the answer of an equation in two variables, is an ordered pair that makes the equation true. So remember, ordered pair is x comma y. That makes that equation true because there's two variables now. So our answers will be ordered pairs that make it true. So in example 1 here, it's kind of quick and easy. It says, tell whether the ordered pair is a solution of the equation. So here's our equation, y equals 2 times x. And we want to check and see, does 3 comma 6, remember that an ordered pair is x first, then y. So we want to see if I substitute 3 in for x and 6 in for y, would it make this equation true? Well, let's try. Let's substitute in 6 for y. So 6 equals 2 times, what was my x? My x was 3. Well, 2 times 3 is 6, into 6 equals 6. So, yes, it does. So 3 comma 6 is a solution. How about for letter B? It says y equals 4x minus 3. Again, remember your x comes first and then your y. So I'll substitute in 4 for x and I'll substitute in 12 for y. 12 equals 4 times, my x value is 4, minus 3, right? So doing a little bit of simplifying there, 12 equals 4 times 4 is 16, and 16 minus 3 is 13. So 12 does not equal 13. So no, 4 comma 12 is not a solution, right? A little bit more vocab here. You can use equations in two variables to represent situations involving two related quantities. Like I was saying before, take a real life event that you have two unknowns. The variable representing the quantity that can change freely is called the independent variable. And the other variable is called the dependent because its value depends on the independent variable. All right, we'll look at some examples, but a lot of times, and I'm not gonna say every time because there are times where this is not true, but very frequently you'll see that the independent variable is represented by your x and your dependent variable is represented by your y. That's only, I would say, boy, it's hard to put a percentage of it, but I'm just going to say most of the time. It's a safe bet. Not always, but a lot of times your x is your independent and your y is your dependent. All right, let's take a look at what that might look like in a real life example. So it says the equation y equals 128 minus 8x gives you the amount y in fluid ounces of milk. So y represents the amount of milk equals, I'm just substituting words in here for my variable, remaining in a gallon jug after you pour X cups. So the amount is equal to 128 minus 8 times the number of cups that you pour. X represents the number of cups. So again, I just substituted these words for that variable. It wants me to identify the independent and the dependent variables. So the independent and the dependent. And again, use the hint that I gave you before, but think about what one of these variables is dependent on the other one. Okay, so in this case, what one is the independent variable? Well, what can change? What can change in the problem, and then what depends on how much you change? Well, what can change in the problem is the number of cups. That's depends on the number of cups is your x, is your x or your independent variable, because the amount poured, it can change. The amount of milk remaining depends on how many cups have been poured. So our y is the dependent, just like I said before, because this, how much milk you have in a gallon jug, depends on how many cups you poured, if that makes sense. But just like what I said before, a lot of times your independent is your x. That's what's changing, and then your y depends on that. Letter B says how much milk remains in the jug after you pour 10 cups. All right, so how much milk remaining, that's y, equals 128 minus 8 times the number of cups. Well, here I've got 10 cups. All right, so if I look at doing that there, I'd take 8 times 10 first. So 128 minus 80. And a little bit of math there, you'd come up with 48. And then, let's see, the label on that would be fluid ounces, OZ, as abbreviation. All right. All right, moving on to the on your own then. Please pause the video now for 1, 2, and 3. And come back to see if you got them correct. All right, number 1, y equals 7x. Okay, for when x is equal to 2 and y is equal to 21. So 21 equals 7 times 2. 21 does not equal 14. So no for number 1, or sometimes the book might say not a solution. Kind of the same thing. Number 2, we've got y, which is 16, equals 5 times x, and in this case, x is 3, plus 1. All right, 16 equals 5 times 3 is 15, plus 1 is 16. So yes, that is a solution. And number 3, a little more practice again with dependent and independent variables. The equation y equals 10x plus 25 gives the amount y in dollars your savings account has after X weeks. All right, so what's going to change here? The number of weeks will change, and your amount in your savings account will depend on how many weeks you've got money in the bank. All right, so just like before, the independent is your X and your dependent is your Y. The amount of money you have in your savings account depends on how long you have your money in your savings account. So that's for letter A. And letter B, how much is in your savings account after 8 weeks? Well, you just have to substitute in 8 for X, because we said the independent variable is the X, and X stands for weeks. So 10 times 8 would be 80, plus 25, Y would equal $105 after 8 weeks. Moving on to the next key idea. In this key idea, we're going to use, and in these few sections here, we're going to use tables, graphs, and equations and see how they all relate to one another. So it says you can use tables, graphs to represent equations in two variables, and the table and graph below represent the equation y equals x plus 2. Y equals x plus 2. All right. So here, all they did is they took different variables for x, and then again, these can change. So 1, 2, and 3 are just random numbers. You can pick any number for your independent variable. As long as you're doing math right, it shouldn't matter. A lot of times using 0, 1, 2, 3 are really nice independent variables to choose. So if you chose 1, 1 plus 2 is 3. That's how they got 3 here. And then they wrote their order pair 1, 3 over 1 up 3, and they put it out. Their second point came from selecting 2 as an independent variable. Again, guys, you could choose any. If you wanted to choose 4, you could. And stick 4 into your equation. Well, that's x, so 4 plus 2 would be 6. So y would equal 6, and your next order pair would be 4, 6. And you'd see it would line up on this line here that they have. So it's a great way to be able to represent an equation. We can take an equation like this, and we can see what it looks like if we were to graph it, and basically find a pattern or a trend. And it's very visual now, which is very helpful for us, rather than just seeing an equation written like this. All right, let's try an example. It says, an athlete burns 200 calories weightlifting. The athlete then works out on an elliptical trainer and burns 10 calories for every minute. Write and graph an equation in two variables that represents the total number of calories burned during the workout. All right, so first we need to write an equation. So I'm going to be thinking what do we want to find? Total number of calories burned during the workout. I'm going to call that C for calories. The total number of calories that I burned is going to equal, well, I did two things. I did some weightlifting, and then I did an elliptical trainer. And during my weightlifting, I burned 200 calories. That was just standard. And so I'm going to add, I also burned calories doing an elliptical trainer. And I burned 10 calories for every minute. But it doesn't tell me how many minutes. So that's going to be my next variable. 10 calories times every minute. Well, I don't know how many minutes, so I'm just going to call that M. So here's my equation. All right. To graph the equation, first make a table and then plot the ordered pairs. All right, so I'm going to be thinking about my independent variable, which is oftentimes x. In this case, it's going to be my number of minutes, because that can change depending on how long I'm on the elliptical. So that's minutes, and I'm going to call that m. Most of the time, it's your x. Here I'm going to write my equation that I came up with. So C equals 200 plus 10 times m. And the next one I'm going to write what I found. So how many calories. So this is where I put my dependent variable, or in this case it's calories, or that's represented by a C. And lastly, I'm going to come up with an ordered pair from that table. So I'll just write that in. My ordered pair would be M, comma, C. First is my independent, and then is my dependent. All right, let's try some different numbers here. And it doesn't, you can choose anything. Remember, choose any number here. It doesn't matter. I like to try to think about different situations in real life that might make this make sense. So I'm going to say maybe one day I'll work out and I'll jog on an elliptical 10 minutes. And another day I'll do it 20 minutes. And if I'm feeling ambitious, I'll do it 30 minutes. Those numbers kind of seem easy and kind of make sense to me. Now I'll plug in these different values for m in my equation. So the number of calories would equal the 200 I burned from weightlifting plus the 10 for each number of minutes that I did it for. Well, in this case, I picked 10. Right? So all you're doing is substituting in your m in this equation. So you can do that for these ones. C equals 200 plus 10 times, in this case, 20. And lastly, 200 plus 10 times 30. Now I'll find the answer to that. I'll find the number of calories that I burned. For my elliptical, it'll be 10 minutes times 10 calories per minute would be 100 plus 200 gives me 300. 20 times 10 would be 200 plus 200 would be 400. 10 times 30 would be 300 plus 200 would be 500. All right, so now my ordered pair would be M, which was 10. And what did I find for calories burned when I jogged for 10 minutes or was on the elliptical for 10 minutes? Well, I burned 300 calories. So I'm just taking my independent and dependent variables and writing them as an ordered pair. 2,400. And lastly, 3,500. Okay. There is my table. Again, choosing random, well, kind of random independent variables and finding out the number of calories burned from there. Lastly, I need to graph that. All right, I'm going to choose a different color here. I'm going to make my X and my Y. Okay. All right. My independent variable, or my X, I chose minutes. And my dependent, for my Y, I chose calories. It's nice to label your X and Y axis. All right, and then I need to figure out, what do I need to go by? Well, here, for my minutes, or for my independent variable, I have 10, 20, and 30. So I could really easily just go by that. 10, 20, 30, 40, 50, and so on. And for my calories, I've got 300, 400, 500. So I could go by 100. So 100, 200, 300, 400, so on and so forth. I'm just going by hundreds. It's okay when you graph. if you go by different values on your x and different values on your y. That's just fine. All right, so my first ordered pair I need to graph is 10, 300. So when I worked out 10 minutes, I burned 300 calories. There's your first plot right there. 20 minutes was 400 calories. So over 20 up 400. And 30 minutes was 500. Okay, so there is my line. Try to make it as neat as possible on this sketch pad. And now I'm graphed. I'm complete. I'm finished. I've got a table and I've got a graph. And now I've taken this real life problem and I can visually see what happens as I work out more. The more minutes I work out, the more calories I burn, which makes pretty good sense. All right, here is the last section that we have for today. And we're talking about the distance formula. It says you can model many rate problems by using the distance formula. D equals RT. I might circle that if I were you. Where D is the distance traveled, R is the speed, and T is the time. When you are given a speed, you can use the formula to write an equation in two variables that represent the situation. So to find the distance, multiply the speed R times the time T, and that'll tell you the distance you've gone. This is the true distance formula, and it's used a lot in physics, actually. So for the example, it says a train averages 40 miles per hour between two cities. Use a graph to show the relationship between the time and the distance traveled. All right, so first thing that we'll do is we'll use a ratio table, kind of similar to before. And you can use a ratio table and multiplication to find equivalent rates. Some of you just did this before in chapter 5, and then plot the ordered pairs from the table and draw the line through the points. So we know that let's think about our labels. We're talking about time, and that's in hours. And we're also talking about distance, and that's in miles. And we know that it averages 40 miles per hour. So in 1 hour, how far has the train gone? Oh, 40 miles. Okay. 1 hour, the train has gone 40 miles. Well, let's think about in 2 hours. How far has it gone? Well, times by 2 would give us 80 miles. All right. You can keep going with that. You could say, you can plug in different points here. Okay, let's say 4 hours. Well, from 1 to 4, I multiply by 4. So to keep this ratio equivalent, I'll multiply by 4 on bottom. Would give me 160. You can keep going. However many plots you think you need to get some accurate data. Maybe say you went 6 hours. How far could you gone? Well, to go from 1 to 6 times by 6, do the same on the bottom. Will give you 240 miles. Okay, lots of different ways that you could represent that in a ratio table. Okay, let's try another way. Let's think about an equation in two variables like we just did in the previous problem. All right, let's start off by saying, thinking about our our different pieces that we need to add to this chart here, or to this table. Again, I've got time, and that was in hours. I'll abbreviate that T. And again, that's my independent variable. That's that my dependent, my miles, are going to depend on how long I was on the train. So here I'll write my equation. So, well, remember the distance equals my speed I know is 40 miles per hour times the time that I was on. And that'll tell me how far I've gone. So that's distance, or in other words, D. I'll abbreviate it. And lastly, again, just like before, my ordered pair. And in this case, it's going to be T, comma D, not XY, but it's really similar to before. So for my time up here, I'll just keep it the same as my ratio table that I chose up here. I did 1 hour. Oops, sorry. I did 1 hour. I did 2 hours. I did 4 hours. I did 6 hours. Doesn't matter. You can choose here. So the distance is equal to 40 times the time. So distance equals 40 times 1. Distance equals 40 miles per hour times 2 hours. Or maybe I'm talking about a situation with 4 hours or 6. Okay, 40 times 1, the distance traveled would be 40 or 80 or 160 or 240 miles, just the same as what I have up here from my ratio table. Now I'll just use that as an ordered pair. So for every 1 hour, I'd go 40 miles. For every 2 hours, I'd go 80 miles. If I was on for 4 hours, I'd go 160 miles. You're kind of hopefully picking up on the trend here. All right? But if you look up here, these are my ordered pairs in the ratio table, similar to how I did it in my table down below. Now I'll just graph that. Right, so here's my y-axis. And in this case, my y, or my dependent variable, was my distance. My x, or my independent variable that I could choose, was time, and that was in hours. I should probably put miles here as well. Okay. And my ordered pairs for 1 hour, well, let's look here for my labels. I could just go by ones here on the bottom, so I don't need to label then when I'm going by ones. And how about for my distance? For my numbers here, well, again, I was going 40 miles per hour, so a lot of times that's a good hint as what you could go by. So 40, 80, 120, 160, so on and so forth. All right, 1 hour, I went 40 miles. 2 hours, I went 80 miles. 4 hours, 1, 2, 3, 4, I went 160. And 6, so 5, 6, I went 240. So this would be 200 and then 240 right here. And you can see we've got a nice linear line. Pretend that I actually connected those dots. But what that is representing is that I'm going 40 miles per hour. All right, that does it for section 4. Again, the biggest thing that I'm doing here is I'm taking equations and I'm making them visual and putting them in a real life situation with a graph, so it's a little bit easier to see. If you have any questions from this section, please come ask me, and I'll see you next time.